Thanks everyone for being here, and we're going to go ahead and get this seminar started. This week, the title of our department seminar is Advancing Reactor Development and Deployment Through Model, Simulation, and Experiment. And our speaker this afternoon is Dr. David Pointer, who is the section head for Advanced Reactor Engineering and Development for the Nuclear Energy and Fuel Cycle Division of Oak Ridge National Labs. At Oak Ridge, he leads a diverse team of experts in R&D activities supporting accelerated deployment of new nuclear energy technologies. And prior to that, has served as the deputy lead for thermal hydraulics methods within CASL, which you all should be familiar with, and as the technical integrator for the Nuclear Energy Advanced Modeling and Simulation program, or NEAMS. Dave received his PhD in nuclear engineering from the University of Tennessee in 2001. And I don't know, have they opened up the new building yet, Dave, or are they still, you know where they're at with the new building?
I don't know where they are with the new building. That's actually a really good question. I know they haven't opened it up yet, but I don't know how close they are.
Can't beat the location, that's for sure.
That's right, for sure.
Yeah, you should definitely do your recruiting on game day. You guys hopefully the new head coach draws a crowd for if the football team can't draw a crowd, maybe the nuclear engineering program can. Anyways, with that, go ahead. Sorry.
I just started to say I'm not sure recruiting on game day is a good idea.
Well, anyways, with that, Dr. Pointer, the floor is yours, and definitely I'd like to thank you for being here today. Thank you.
Well, thanks for the introduction and thanks for the invitation. I'm really excited to have the chance to talk to you and about the work we're doing, and look forward to your questions and comments. I think feel free to interrupt me if you have questions. It's hard to see, not always easy to see hands going up, so feel free to yell at me if I'm ignoring you on the Zoom. And I think I've had a lot of interesting opportunities in the 20 years I've been at the labs, and I'm really most excited about the current one, but that's probably always true. Otherwise, I wouldn't still be at the labs. Once again, I find myself in a position that has a really long name that's a mouthful to say, but it's been really exciting to learn about the capabilities that this new section at Oak Ridge has to offer the nuclear industry, and to help start to chart a course, for the future of our work and our efforts to help facilitate deployment of some new advanced reactor systems here in the U.S. And we'll see if I can successfully advance my slides. As most of you know, Oak Ridge was home to the world's first continuously operating nuclear reactor during the Manhattan Project, and it was very quickly deployed. There was a decision to start construction on this project in February 1943, and the entire project was completed in about 9 months. The graphite reactor is even actually more remarkable because the reality is the design wasn't even close to done. The original designs used coolants other than the air that was actually used in the final design, looking at helium and water options for the cooling of the reactor. The reality is, even though they were approved in February, they didn't actually start the initial excavation for the reactor building until April of 1943. It was even a shorter timeline to go from the start of construction to real construction to actual operation in July 1944. It's just unfathomable today to pursue a reactor project, even a critical experiment, where the timeline is this short. It's not clear when we deviated from the ability to do something quickly, and it's not really clear why, but it's clear that it happened very early in the life of nuclear engineering as a discipline. Because if you go forward to 1962, which is not that far ahead in the grand scheme of things at this point, the design, development, and construction of the molten salt reactor experiment already took 5 years. It's not a significantly larger facility. The power levels are about the same. it's a fairly small core. You can actually see half the core it's being assembled in the photo on the right-hand side. The timeline is much longer. Construction started in early 1962, and we didn't get to the initial criticality until 1965 at very low power operations. And we didn't hit full power until almost a year later in 1966 for a variety of reasons. We'd already seen a massive slowdown in our approach to deploying new reactor technology, even in the 1960s. There's a lot of reasons we think, a lot of things that really we think contribute to the slowdown and the continuing slowdown of deployment timelines for reactor technology. And the focus of our group, the Advanced Reactor Engineering Development section here at ORNL, is really on trying to push back the other direction. We want to enable U.S. industry to bring innovative technologies to market with much greater speed and with more confidence in both the safety and in the cost effectiveness of their solutions. And we're leveraging a lot of world-leading infrastructure and capabilities in the laboratory to try to do that. And that's what I'm going to try to tell you about for the next 40 minutes or so. A lot of our work in the national laboratories has been driven over the last decade by the realization of some long-term goals in the availability of computing power. The top 500 list was established in 1993 and started tracking the computing power of the world's fastest machines, wherever they may reside, looking at the top 500 of them, based on the number of floating point operations per second that they can complete, or the number of flops associated with the machine. And you can see back then we were talking about machines that were in sort of the 10 billion floating point operations per second range, which was deemed a remarkable breakthrough actually at that time, because it had been a quick ramp up from some things that were a factor of 1,000 smaller. And that was really the initial driver for interest in high performance computing as a solution to a lot of engineering and science problems. Because we saw a timeline that was not centuries, but decades to get to very large scale computations that were previously just completely impossible. And we have continued to progress in sort of a linear fashion, in a sort of exponential fashion here, that was expected, at that time in 1993, and it's actually gone on longer than we might have anticipated. So the data that's shown here in blue is the number one computer in the world as a function of time, and the data shown in the red triangle is the number 500 computer in the world as a function of time. And you can see how we've sort of evolved the infrastructure for computing worldwide over the last 3 decades. And it's been a remarkable change. If I go back to when I first joined the laboratories in the early 2000s, the machines that were available for high performance computing were really almost completely inaccessible. They were often tied to national security programs rather than open science programs. And it was really in the early 2000s when there was a large push worldwide, not just in the US, to make a shift in those investments so that more machines were available for open science. If I think back to my early career as a graduate student, I was working on those DEC Alpha and Spark systems that you see down at the bottom of this chart. And those were not inexpensive purchases. We were spending hundreds of thousands of dollars on each of those workstations to support simulations work. Now they're really kind of laughable because the phone in my pocket's several thousand times faster than that multi-$100,000 workstation was in 1997. The key here, takeaway here, is that we've been on a rapid increase in computing horsepower, and it's really enabled a lot of approaches that were just not possible 2 decades ago. And we're going to continue to leverage that going forward in a lot of ways. Back in the early 2000s, as we were talking about the startup of what became the NEAMS program and then led to the CASL program. We talked a lot about the challenge of multiphysics analysis. This is a famous chart that was put together in a paper in 1980 by Ken Lassman to describe how all the different physics that play a role in fuel performance interconnect with each other. And you can see this is what we call now referred to as the spaghetti diagram, because the interconnections are insane. They're just every individual characteristic that you can evaluate is tied to at least 4 others, and either as an input or an output. So any approach to modeling a fuel system really requires that you get your hands around all of the different physics at one time. The same thing is true for reactors. This is a vision for reactors that we put together back in around 2010 to try to understand what you would have to couple if you wanted to provide a more comprehensive multi-physics analysis capability for a nuclear reactor system. And as you can see that there's a lot of connections here as well. In the CASL program, we have focused on integrating a set of tools to address this multi-physics problem for light water reactors. CASL was established now 11 years ago, and was driven by a set of 10 key partners, core partners, including NC State, that worked to address the challenges of extending the life of light water reactor cores and getting more power out of the fuel that we put in over the coming decades. We did this in an unusual way, driven by a board of directors and a science council that identified key challenge problems and then kept us honest in our attempts to address them, which was very unusual for a DOE program. This is really sort of the biggest lesson learned from the innovation hubs that were established at this time. And it continues to influence the way DOE approaches a lot of its work today. So the main product of CASL under this leadership was a package that we call VERA, the Virtual Environment for Reactor Analysis, which brings together a set of key physics codes for evaluation of reactor physics and isotopic depletion, the chemistry of the coolant, the evaluation of thermal hydraulics in the core, and then individual fuel rod performance, so that you can then pick and choose and plug and play in a way the physics that are important for a particular problem, and generate a tool set that can be used to answer your questions about how to improve that system. So for evaluation of fuel performance, you might focus on the collection of 4 codes shown on the screen, using Origin for isotopic depletion, Impact for neutronics, Bison for fuel performance, and CTF for thermal hydraulics. And you may reconfigure your system to evaluate Crud-induced power shifts in a PWR, using the neutronics and depletion capability and the thermal hydraulics capability, but tying in Mamba instead of fuel performance to evaluate the chemistry of the coolant in the system. We've applied this set of tools to a lot of problems over the life of the CASL program, and probably one of the most important was evaluation of the Watts bar Unit 2 prior to startup, and then running essentially in real time a virtual twin of Watts bar over its startup cycle to try to help TVAC better understand what they were observing in the startup of the plant. So this is the power history from the power Ascension testing before the full startup, and you can see that they go through a lot of transients with planned load rejections, tests of turbine trips, and the evaluation of the safety systems as you come up to full power, and ending with that 50% load rejection there. The VERA team demonstrated that you could follow along this process based on input of real-time data, and correctly follow the boron concentration in the PWR. The power level is controlled by boron through the boron concentration in these startup tests, either diluting or adding additional boron to the coolant. And here the codes were used to predict the level of boron required to obtain the desired behavior and the level of boron observed based on the feedback. And you can see we did really well predicting the measured boron concentrations. Another important test was a benchmark against a Crud-induced power shift. In this challenge problem, the Crud layers form on the upper regions of high-powered rods where nuclear boiling occurs, and it's driven by the metals that are leached out of your heat exchangers and pressurizers and all of the metallic components in your system that are then deposited as oxides on the fuel rods as a result of the boiling process there. And so boron from the coolant ends up being deposited in this Crud layer. It happens preferentially because of some key chemistry of the Crud as it forms, and under certain conditions. And then the boron initially suppresses the power at the top of the core as it builds up. So the outcome is that the fuel depletes more at the bottom of the core. That causes a very undesirable power shift from the mid to the end of the cycle, middle of the cycle to the end of the cycle, and ultimately reduces the lifetime of the fuel assembly. And so here on the bottom left, you can see a plot of the measured axial offset from an actual plant in red and as red dots. And as a function of the cycle, a function of the burnup of the fuel, and the blue diamonds are showing you the standard prediction from standard industry methods that would be used to guide an operator through this expected cycle. And the green squares are showing the results from VERA. So you can see we get a pretty substantial improvement in the prediction of the actual axial offset using this more complex and multi-physics analysis capability. There's still a lot of places where we can do better, and those are largely improvements that are needed in the reabsorption of boron from the prediction of reabsorption of the boron from the Crud back into the coolant. But those are things that are still in progress in the follow-on activities beyond CASL. Multiphysics is not the only challenge. We also have a spatial and temporal scale challenge in that the individual physical phenomena that drive reactor behavior span an enormous range of time and length scales. If we think about the most fundamental atomistic behaviors in a nuclear reactor core, things like formations of defect clusters in the fuel and the nucleation of individual bubbles happen on very short time scales and very small length scales. But then the performance of your containment in holding back a source term during a severe accident happens on very long time scales and very long length scales. And so we have to think about how to transition from the very short lengthened times to the very long lengthened times. And that's not really easy. We've done this historically by putting an engineer in each one of these boxes and asking that person to hand off data from one to the next. And then you hope that the collection of engineers all are really good at integrating information and provide you with an integral outcome that represents the behavior of your system. So we match that sort of spread of length and time scales with a spread of tools that cover each of those that all have their own independent boundary conditions, their own independent inputs, their own independent solution methods. We're relying, here again on the expertise of the individual engineer sitting in that box to make the connections. Within CASL, we started thinking about how well, within the precursors to DEAMS and CASL, we started thinking about how to address that problem for some of the individual physics. And I've been showing this inverted triangle for the thermal hydraulics part of the problem for most of the last 20 years, probably starting back in 2004, when we started talking about how you move data from 0 and 1D lump parameter codes like RELAP5 or Trace up into were coarse CFD methods for evaluation of individual components. And now that's grown radically to encompass tools going all the way to direct numerical simulation, where you generate essentially raw input data to build better engineering models in the coarser tools. And so a good demonstration of that, really what I think has been the best demonstration of that, and I'm completely biased because I was part of it, has been the development of RothCon as a method for CFD-informed high-to-low modeling in the Cobra TF code in CTF. And here we work to demonstrate that you could take a high-resolution CFD simulation of the behavior in a PWR fuel assembly, and in this case, it's a 5x5 reference bundle that we've used for a lot of problems in CASL, rather than a real full-size assembly. But we want to take the information from that very data-rich CFD model and use it to improve the predictions of CTF. If you look at the individual subchannel regions that are defined by the dashed lines, where you end up with these square and rectangular segments, CTF is going to predict one temperature at every axial position inside this box. And you can see a comparison of the CTF subchannel temperatures. I'm going to change that to a pointer so maybe you can see it a little better. And if you look at the CTF predictions of temperatures in those individual subchannels versus the CFD predictions of temperatures in the individual subchannels, the average CFD prediction of temperature in this region, you can see we actually get pretty good agreement. They agree with each other pretty well, whereas each one of these lines is really moving from the inlet of the assembly to the outlet. And we've differentiated between the corner and site and inner subchannels here. But they agree pretty well, usually typically within 5% of the measured temperature or of the expected temperature from either code. But if we look at the more detailed information that comes out of the simulations, if we just pick one rod here, in this case, the axial rod, axial temperature profile of the rod here in the center, you can see that the CTF prediction is this nice flat line that's a single data point at every axial location. Whereas the CFD simulation is predicting this rich data set that describes the axial distribution of temperature around the individual pin, which is information that's thrown away. The nice thing is that we can observe from this plot is that the CTF prediction is generally conservative and typically predicts a higher temperature than the maximum, which is what you want to see in a code that may be used to impact safety decisions. But we're throwing away all of this additional detail, which would be extremely valuable to the evaluation of crud growth in the system. So we've taken this center pin, this pin 25 at the center of the bundle, and unrolled it. And so this is, in this plot, the vertical direction is the axial direction of the pin, and the horizontal direction is the distance around the pin. And we're showing here the heat transfer coefficient map on that pin surface from the CFD model. We've then used this information to create a calibrated projection model that takes the predictions for pin 25, this line from CTF, and recreates this richer data set of azimuthal dependence using a projection model. This is very analogous to the approach that we would take in neutronics to go from pin power calculations to lattice calculations and back with pin power reconstruction. And if you look at the chart here on the bottom right, you can see that this is the root mean square error in the uncorrected prediction of temperature, and this is the root mean square error in the reconstruction. So you can see that we bring the CTF prediction of temperature back much closer to the CFD result using this calibration approach. And this has really been the first truly successful demonstration of CFD-informed model development, using a very indirect data integration approach, a hierarchical data integration approach. And now we're working on ways to make this much more direct, relying on artificial intelligence and other means. So I've told you all of that to kind of give you a picture of where we are today in the development of digital twin methodologies for advanced reactors. But the reality is, the impact of all of this work to understand the multiphysics behavior of cores only goes so far in impacting the cost and timelines of deploying new nuclear technology. If we look at the cost of nuclear deployment, the cost of the nuclear island itself, the equipment that goes into the reactor core and the building that's going to house it, is isolated to this wedge of 13% of the reactor cost. And the vast majority of the cost is associated with sort of the large scale construction project of building a facility of any kind of this size, working on the yard and the cooling, and all of the installation of buildings to support the reactor. That means that anything we do using VERA to impact the core and fuel is isolated to these little wedges up here, the nuclear island construction and turbine island equipment installation, unless we think bigger picture and look at how the decisions we make in these areas impact the cost of installation and site prep, as well as this important box over here that's the cost of money for the owner, who is going to have to finance this project to build a reactor. If we look at the objectives that have been laid out for small modular reactor and now micro reactor or fission battery programs, there's a lot of commonality, and it's largely focused on making these systems much more cost competitive. The goal is to be flexible and enable electricity or process heat to be produced, so that you have variety of in-use application that makes use of the power. This is probably a much smarter model than thinking about load following a nuclear system. The goal is to make them standardized, to simplify licensing processes. We want them to be, as much as possible, to be factory made, to take advantages of cost reductions in factory construction versus construction on site. The goals that are plug and play. You don't have to really do a lot of customization of site plans for the system that you choose. We want them to be as autonomous as we can make them. Within our section, we talk about making reactors so smart they don't need us anymore, and that's really an ambitious goal. They have to be fault tolerant. We have to reduce our security footprint. We can't continue to support the enormous security force that's required for conventional LWRs, and we also need to reduce the emergency planning footprint, which has large regional impacts on cost for local governments, and maybe a disincentive for communities to embrace the rollout of additional nuclear systems. And then finally, we want to make sure that everything we build is reusable as possible, or at least used for extremely long periods of time, which is important to consider in nuclear battery concepts, which may be shipped to a site, used for a short period, and returned to a vendor for service. In order to address those economics, we really have to move beyond the core. And there are a lot of technologies that we can use to be more integral in our thinking about the life cycle of an individual plant. The core is the small structure that resides in the reactor building there, in the containment building. But there's a lot of other stuff that goes into building this site and connecting it to the grid, and then planning for its operation over a long period of time. And then ultimately either demolishing the site and going back to greenfield, or doing some sort of renovation to continue operating. So a big part of that, in our minds, is that embracing digital twin technologies and supporting their deployment for nuclear systems. Digital twins are really an integration of three major areas of technology development that have grown over the last decade. Probably the most important is the growth of model-based system engineering as a strategy for optimization of not just the design of a component, but of the design of the system that you're going to deploy and its connections, all of its connections to the end users. This goes hand in hand with product lifecycle management strategies, which help to get a handle on the role of all of your suppliers and the steps that you're going to take over the life of a facility to keep it performing at the level that you expect. And then finally, the other major contributor is the Internet of Things approach, where we have a lot of sensors that are producing a lot of information, and we don't make use of a lot of it. A lot of it's there collecting information to warn us if something has gone wrong. But there's a wealth of information that comes from those sensors that already exist in these plants that we could be using to make better decisions about maintenance strategies. And if we look at future plants that we want to roll out, if we really are successful in deploying more distributed sensors, and we have a lot of ideas about how to do that in these new facilities, there'll be even more information. And in fact, the challenge, for a nuclear system is that they're so complex and there's so many moving parts. It's really an unmanageable job for a person. That's why we haven't taken as much advantage of many of these data streams as we probably should have. But advancements in artificial intelligence are really a key enabling technology to make more sense of the data that we have, and are a key part of building what we would call a digital twin that's more comprehensive than just a core model and considers sort of the bigger picture. We want to be able to do things like make predictions of dynamic energy system performance of an entire grid. Looking at what happened with ERCOT in Texas over the last few weeks, clearly there's a need to think bigger than just your local facility and think about how the entire system is going to respond to a challenge. And then, this reaches into other areas that are important. You need to be able to evaluate your risk in real time as you move forward in real life. And dynamic PRA is certainly an opportunity to think about how to do that. We want to make risk-informed decisions about operational planning, and that includes using prognostic health modeling to better understand the performance of individual components and make smarter decisions about when to do maintenance or replace parts of our facility. I talk about the need to make better use of our data, and part of the challenge is just in getting our arms around all of the data that we can generate. There's an enormous number of sensors in a plant today already, and if we're serious about adding many more, orders of magnitude more sensors through distributed sensor networks or through fiber optic means or other ideas that have been evolved in time, we have to decide how we're going to structure that information. And in most industries, the way that's happening is through GIS tagging, so that you know where the data comes from and at what time, and you can tie it in with all of the other data that comes from your facility. So it's becoming increasingly challenging to get our arms around all of the data that's available to us. And it starts with making siting decisions about where to put your reactor. So we have a tool that we've developed at Oak Ridge called OR Sage that helps to manage and interrogate and visualize GIS tag data. And we generally focus on siting questions with this tool. But we see it as an opportunity to bring some structure to the data we might generate within our facilities as well. I want to show you another important tool that has evolved largely from investments in the hybrid energy systems programs of DOE as a way to evaluate dynamic performance of systems. So Transform is a library of connectable multi-domain models that enable rapid modeling and evaluation of different deployment scenarios. And since the music is actually turned on, I'm going to stop talking and just let you watch, and then I'll catch up. Okay, so as I was saying, Transform has been largely developed within the Nuclear Hybrid Energy Systems program, and it's structured in such a way that you can build very large, complex models of any energy system. And the Transform components are a library of components that are specific to nuclear energy deployment, as well as some of the things that sort of go along with that, like components for for desalination and hydrogen production and some energy storage features that are specific to our problems. But it's important that it's a library and not a code, as we would think of them in the traditional sense at national laboratories and universities for nuclear applications. Recognizing that there are dozens of solutions that companies have for commercial products to solve simple system level problems, simple PDE solvers. We have developed a library that is Modelica based. Modelica is a high level programming language that's very compatible with most of those commercial solvers. We use it within Dassault's Diamola environment, but it's also compatible with the tools produced by Siemens and others. And so it allows you to very quickly assemble a very complex model of a reactor or a energy generation component of any kind. And we can use the nesting features of the tools to look at how they interact with each other. So we can look at large scale deployments that include wind and solar and energy storage, as well as nuclear components. And we've done those studies for a few sites as part of some demonstration projects. Most recently looking at a deployment with the Tennessee Eastman Chemical Company in Kingsport, Tennessee, where they're interested in potentially replacing some of their thermal energy source and electric energy source with nuclear power in the mid to long term. Transform is really key to a lot of our vision for how to address the big picture cost and acceleration of deployment problem. The work that's been going on in the last few months has been focused on integration of these tools with VERA so that you can leverage that high resolution representation of the core. And we've started with inclusion of a VERA model of the core of MSRE into our large scale Transform model of that reactor, just as a way to demonstrate the integration of these tools. There's a ready-made feature within the sort of Modelica world that focuses on a standard for integration called FMU or FMI. And I won't get into that. We can talk about it more if you want. But we're leveraging that to be able to quickly integrate additional tools. And there are now libraries available to make those couplings to Transform either through C++ or Fortran for current or legacy codes that we may want to couple. We've done a lot of work to tie these capabilities to sensitivity analysis tools, and you can work with either Raven or Dakota to do sensitivity analysis or uncertainty quantification. And this is an important feature, since a lot of the work we want to do is evaluating the performance of different systems in a wide variety of scenarios. And these tools provide the drivers for considering all of that. We've also integrated our modeling capability in Transform with our dynamic PRA capability within the section, and are now able to do reliability-based evaluations of the expected lifetime of individual components. In this case, we're looking at a turbine control valve. And this is really a first step toward being able to do optimization of maintenance cycles for individual systems. And it ties into our work on the instrumentation and control side in enabling us to move from just sensing to doing active prognostic health and risk assessment as part of any control system, so that we're evaluating the expected lifetime of a component based on real-time data using the same methodology, and then ultimately tying it into the control logic and decision making that may eventually lead to actuation through autonomous control. This is the pathway to autonomous control and operation of a reactor. I'll just mention that that our colleagues at NC State are an important part of making this real And we look forward to continuing to work with you on these problems. A big piece of the puzzle for being successful in enabling this kind of active prognostic decision making in both the control of the system and in managing the plant and managing the operations of the operations and maintenance of the plant is improving the robustness of, or improving our confidence in the information we're getting from our sensors through a more robust method for detection of drift and detection of failure in the sensors that we rely on. And while the digital twin is serving as a way to consolidate all the information from individual sensors for an operator, it also serves as a way to detect sensor information that seems to have gone astray, because we have a reference point that tells us what we should expect. If we see all of the sensors moving away from the expectation, then we know something is wrong with our model or something has gone wrong in our facility. If we see one sensor drifting away, then we know we have a problem with that piece of equipment. And so this is a sort of next step evolution in our approach to sensor drift management in large complex facilities. Another important piece may be the ability to begin making robust predictions of time to failure for individual components. And here I just show an example looking at the fatigue crack initiation in a component, but there are many applications of this sort of strategy for all of the individual components of a reactor. And of course, we would want to start focusing primarily on the big ones that are risks to either safety or continued operation of the asset. And so fatigue crack initiation is a good way to start to break into that ground, and has been our focus. I mentioned early on in my slides that we're really excited about the Internet of Things concept, and we spent a lot of time at the laboratory thinking about how you develop new sensor technologies that may be very widely deployed within large facilities. And we're also beginning to think about how we integrate that information from the very beginning of the life of a component. And so the Transformational Challenge Reactor is a project that some of you may have heard about with the ambitious goal to 3D print a reactor core, and to do that over the next 4 years for an operating reactor core. The guiding principle here is to use artificial intelligence to help navigate the unconstrained design space and do more open optimization of a core concept that's made possible by the advances in additive manufacturing methodologies over the last couple of years, especially for a wider variety of materials that are important for reactor systems. But not only to leverage the AI for the design of those, but to actually better understand the quality of the component that you're producing, and make some projections about expected lifetime based on measurements that are made in situ while you print the part. And those may be indirect observations with cameras that are focused on the system, measuring temperatures and the physical dimensions of a component and their changes in time over the life of over the cycle of production of the part. Or it may also include embedding sensors within the parts. And we're very interested especially in embedding fiber optics within the parts, so that we're able to make measurements in real time as the parts are built, and then use those same sensors as measurement methods in the core. And so this is really an exciting development. It starts to bring together some of the evolutions in technology outside of nuclear for a big impact on nuclear deployments in the very near term. I'll start to wrap up here and just acknowledge that I haven't done much of this work myself. Instead, I spend all of my time trying to understand what all of these really smart people are doing to impact the future of nuclear technology. They all work really hard and are very passionate about each one of these slides that I've talked about. If you're interested in talking further about the details of some of these efforts, I'm happy to connect you to the folks who are really the brains behind the operation here. just to sort of conclude, I think we've made some big impacts with advanced modeling and simulation in the last decade through teams in CASL, and it's given us the opportunity to gain some insights on both design and safety that you just can't obtain from experiments alone, and it's not available from our past experience for a variety of reasons. And it's become more clear over the course of these projects that having an impact on deployment really requires a return to a more holistic consideration of plant design and digging ourselves back out of the hole, of this extreme focus on cores. But it's important that we recognize they provide a springboard toward true digital twins for nuclear systems that we can use to impact those deployment plans. I envision a future over the next decade where all of the simulation technology comes together to let us look at the entire cycle of construction of a new facility in detail and make optimization recommendations based on the analysis. And weighing much more heavily on data than on engineering intuition, as we often do now. And with that, I'm happy to stop talking and answer any questions you might have, or I welcome your comments on the path forward as well.
Thank you very much for an awesome presentation. As usual for our attendees, there are two ways that you can bring questions to our guest. You can either post the questions in the chat and I can be happy to read them off for you, or please raise your hand and I will call on you from the participant list. We did have one question that came up that was asking about the availability of the Transform software and library for use by students, but I believe Dr. Diakonisa has answered that by providing the GitHub link. I don't know if there's anything else you want to add to that.
So I will say that the Transform library is completely available in open source, and we made that decision early on because we thought it was important to have the community's involvement in the development of the individual components, because the application space is potentially so broad. And so, we welcome people are welcome to download the library, and we welcome your feedback and comments and contributions to its ongoing development. The use of the tools is really dependent on the selection of a platform for the solver. The library itself doesn't include a solver, and it needs to be tied to a solution package. We generally prefer to focus on the commercial solutions here at the laboratory because we're very interested in trying to define a pathway that leads us toward NQA1 certification of a tool set. If this were to be used in a deployment evaluation for a reactor. However, there are open source solution schemes available for Modelica and open source libraries for user environments as well. We have not pursued that ourselves, but are certainly interested in partnerships to try to begin to develop those capabilities.
Thank you. Another question that came up in the chat is what are the differences or the relationship between advanced M&S and digital twin?
So there's a lot of talk about digital twins that without a lot of real definition. In my view, a digital twin is a little broader reaching than what we have traditionally thought about as modeling and simulation for engineering systems. It's important that digital twins incorporate real data from real systems, whether it's inline incorporation through Internet of Things type technologies, or it's hierarchical integration like we've demonstrated with CTF and Star CCM Plus with that Rothcon example. It's important that the data integration piece is a major consideration of digital twin development. It also has to be tied to your product lifecycle management strategy for whatever you're producing, whether we're talking about making widgets or building a reactor. The digital twin is only useful if it helps you make a meaningful decision in that pathway. And so I think it's important to recognize the role that the modeling simulation tools play in building a digital twin, but it's not sufficient to focus exclusively on those. And we're trying to broaden that discussion with our work around Transform.
Thank you. Any other questions from the audience? Please raise your hand or post them in the chat. We have one more question from the same, I think it's a follow-up question from the digital twin question. Sure. What will be the verification, validation, and uncertainty quantification strategy for digital twin?
You know, that's a really interesting problem and something I'm personally very interested in. So I'm glad somebody asked. Yeah, I think there's a heavy lift associated with defining a VVUQ strategy for digital twins, because it really reaches out beyond what we have considered in our development of standards for codes. You know, we've produced a lot of documentation through the various technical professional organizations and through DOE programs that define some best practices for VVUQ for a code. But a digital twin is really the integration of a lot of information streams that include some codes, which we hope follow those VVUQ strategies. It includes some data, which we hope has some VVUQ. But I can tell you that the published data that we put out doesn't come close to following the same rigor that we expect from a simulation in a lot of cases. We're also integrating the decision-making strategies of the organization that that define the product lifecycle that they envision. And so there's a lot of information that doesn't have the same level of pedigree that's being integrated in a digital twin. And I think we really need to do some work to understand how the uncertainties in those pieces impact the information or guidance that a digital twin might provide. I hope that we might see some early ideas from the NAMAC project at NC State and from Nam Din's team. But it's going to take us some time to sort through how we approach evaluating the uncertainties and how they propagate through these systems, which are getting more and more complex by the day.
Okay, thank you. Okay, I'm going to give one more shout out to see if anyone has any more questions. And I'm not seeing anything coming up on either the chat or on the participant list. So I'll do my usual going once and going twice. And I believe that the attendees are happy, which is hopefully the guest is happy as well. And we're all happy. And I want to thank everyone for, I'm going to thank that first and foremost, I want to thank our speaker today for a really good talk and really interesting talk. And I want to thank everyone for your attention and your questions, and look forward to seeing everyone next week at our next department seminar. So with that, David, thank you very much. And I'll see everyone in a week, if not sooner.
Thanks for the opportunity to join you.
Thanks.
David.